Okay, so in this segment, I want to direct our attention to the term that I labeled as elastic heating from our equation for heat transport. So I'm going to call this segment, I'm going to title this segment Thermoelasticity. Okay, so all we are doing now is considering this guy, rho 0, theta, this second derivative, okay. I'm essentially going to give you examples, right? We are going to look at not examples in the sense of specific functions, although we'll see that to some extent, but just let's talk about how this can come about. Okay, so suppose we say that chi bar, or properly rho 0 chi bar, function of E and theta has the sort of dependence we'd suggested earlier, right, where we said that there is one term, say C bar, which depends only upon theta, all right, and we have our other term which we had so far been referring to before we happened upon thermomechanics. We'd been referring to the strain energy as being a function only of E, but let us suppose that it too has a dependence on theta. Okay, and the only reason for writing it out this way is that now clearly when we talk about the term that we identified with the specific heat, that specific heat term lives in C bar. Okay, that's all I want to do. I just want to get it out of the way because it doesn't play a role here. Right? The specific heat itself doesn't play a role. So let's just say that, let me just state that, note that C, the specific heat which we defined as being rho naught theta, this second derivative with a minus sign on this, is now, well, it's just minus rho 0 theta C bar double prime, right? Because C is just a function of theta. Okay, that's done. It's out of the way. The specific, that's our specific heat. Okay, all right. Let's talk about the next term now. So really, what we're talking about here is the rho naught theta, the second derivative, right? This is essentially just theta times the second derivative of psi bar with respect to theta and E. E dot. Okay, so I just want to dwell upon the possible sources of this type of mixed derivative terms. Okay, so what are the physicals? What are the physical consequences of something like this, right? Or alternately, what are the physical models that can lead to this type of dependence? Okay, so the first one is if so let's just look at examples. Okay, so example 1. Suppose we have a psi bar, right, which now is a function of theta and E, or sorry, I keep mixing this, E and theta. E and theta, okay. And suppose now that the way that this dependence comes about is that our lambda, let's suppose we are working with isotropic materials, okay? And we wrote our models for isotropic materials in terms of these elastic constants, right? The Lamé parameters, lambda and mu, Well, the simplest dependence is if they are now functions of temperature. Okay, so we have this, maybe we have lambda theta function of E multiplied by some function of E plus mu theta function, G function of E. Okay, for isotropic materials. Actually, that's not necessary. I don't need to state that actually. Let's just consider a model of this type, right? And you can see if you wanted to go on to more general material models, you would just add more elastic constants and so on. Okay, so if you now go back and look at least the 3 isotropic material models we considered, and in fact even the Samanon-Kirchhoff model extended to anisotropy, you will very clearly be able to identify f of E and g of E. Okay, those are just some other functions of the strain, where now we have all the temperature dependence sitting in the moduli. Okay, it's very clear from here where we get this sort of term from, right? So now clearly that second derivative right, it just comes about by saying that now we have lambda prime function of theta partial of f with respect to E plus mu prime function of theta partial of G with respect to E, right, the whole thing contracted with E dot. Okay, all right, and and in this case lambda theta and mu theta are the so-called adiabatic elastic constants. Okay, they're adiabatic and not isothermal, because if they were isothermal, then derivatives with respect to theta would not be allowed in the processes we're dealing with. Okay, and it's pretty obvious what this models. This essentially models a process of elastic softening, which must happen with all materials as their temperature is raised. Right, so this is what we would call elastic or properly thermoelastic softening. Thermoelastic softening. Okay. All right. The second example is actually much more interesting to me. Okay. So the second example is one in which we are saying that psi bar of E and theta depends not through the elastic constants, depends upon theta not through the elastic constants, but through something else. Okay, so we're saying that the elastic moduli, the elastic constants are independent of temperature, but we can still have this dependence. And here's how we do it. This essentially is what this sort of an approach is what we need to model thermal expansion and contraction. Okay, so So let me state that thermal expansion, okay, and contraction, of course. So here's the idea. Let's suppose that we have our body here in the reference configuration omega naught, okay, and we want to okay, and we have a some neighborhood, right, of the point x. The process we want to model is one where that neighborhood expands or contracts through thermal effects, okay. So let us suppose that we consider that in the first step the system goes to, let's model expansion. Let's, at least to fix ideas, think of this as expanding, okay, right? And then after that it undergoes what we may call an elastic part of deformation, okay. So because I want to think about this as being thermal, I'm going to write the first part of the deformation gradient as f theta, right, and then we have Fe, so that now in the deformed configuration that little volume element has maybe swollen a little and perhaps also deformed. All right, and the composition of these two gives us the total F. Okay, so the way we would write the total F here, the total deformation gradient, is F equals F theta, F E F theta, okay, as a multiplicative decomposition. Okay, so we have a multiplicative thermoelastic decomposition of F. Okay. So let me be very specific and straight away write out a model for this. Okay. So what I'm saying is that we have F equals Fe F theta, just reproducing what I had there. And so, you know, we typically tend to think of the kinematics of thermal expansion as being isotropic, right? So this is our body and it is going to expand. This is our body, it's going to expand. We tend to think of it as just swelling if the only thing that's happening is thermal expansion or contraction, right? It's just going to expand or contract isotropically, maintaining its shape. So let's represent that, okay? So if we say that theta now is some function h of theta, okay, to the 1/3 power, okay, multiplied by the isotropic tensor. What we have here is isotropic expansion, where h of theta is the thermal expansion volume ratio. Right, and it's pretty clear why this follows, because now if we take the determinant of this part of the deformation gradient, we see clearly that it is just h of theta. Right? Okay? All right. So now we can say that, our strain energy density function, which we previously thought of as being a function only of E and theta, we can now write it as by saying that, well, we want to think of elastic energy as being stored only in Fe. Okay? So we want to think of this entire function as something where this thing stores elastic energy only due to Fe, right? The elastic part of the deformation gradient. Okay? Okay, F theta being the thermal part of F. Okay, and how could we do that? Well, we can say that, from Fe, we write Fe transpose Fe minus the isotropic tensor. Take 1/2 of this. Okay, right? We observe that from the sorts of decompositions that we have up here, we can write this as 1/2. Okay, now Fe transpose from this relation we can write as h to the minus 1/3 F transpose F times h to the minus 1/3 again. Right? All I've done is to essentially rewrite Fe in terms of F and our thermal part of the deformation gradient. Okay, minus isotropic tensor. All right. Okay, so here we are, and now let me just work with this just a little more. 1/2 of h to the minus 2/3 C, because that's F transpose F, minus the isotropic tensor. Okay? Now, we can write this as 1/2 h to the minus 2/3. Now, you recall that C can be written in terms of E, the Lagrange strain tensor, as 2E plus the isotropic tensor. Okay? And then we still have the minus isotropic tensor. Okay? And remember that this is a function of theta all along. Everywhere h is a function of theta. Okay, so when we continue with this, we see that we get, here we get h to the minus 2/3 function of theta E plus 1/2 h to the minus 2/3 function of theta minus 1 isotropic tensor. Okay? Now, we can legitimately call this quantity, which we had on the left-hand side, the elastic part of the Lagrange strain tensor, and we are saying that it has this dependence upon the full Lagrange strain tensor and upon the temperature. Okay? Okay, so now the approach that is going to be followed is to write out our strain energy function as depending only upon this quantity, and I notice that I have a slight algebraic mistake here, which I think is fixed if I do that. Yeah. Okay. So we're going to rewrite the strain energy function as depending only upon the elastic part of the Lagrange strain tensor. And the way we do that is to say that now psi bar of E comma theta can be now written as some other function which now depends only upon the elastic part of the Lagrange strain tensor and is in fact psi bar E of h to the minus 2/3 depending on theta multiplied by the by the full Lagrange strain tensor minus 1/2 h to the minus 2/3 depends upon theta minus 1 isotropic tensor. So what we have here is a model for a material that has thermal effects in the sense that it is expanding because of local temperature changes, but stores energy only because of superposed deformation. Okay, so if this material had no superposed deformation but were just free to expand as driven by the temperature, there is no reason for it to store elastic energy. Okay? All right? In that case, what we would see is that the elastic part of the Lagrange strain tensor would be 0. Okay? And the material would not store any more energy. Okay? But having written out the full elastic part of the strain energy function in this form, the form that we have here, okay, we have clearly now a dependence upon E and upon theta. Okay? So for a material such as this, it is pretty clear that this sort of derivative psi bar with respect to theta with respect to E will arise. Okay? So this is a case where so this term is not 0. Okay? So this is a case where this contribution to the elastic heating comes from the fact that there is this phenomenon in which the material expands as a result of local temperature changes. Okay? So this is another example of how thermoelasticity works, modeling a phenomenon of thermal expansion and contraction, which you are all definitely familiar with. Okay? All right, you stop here.